Okay, so welcome everyone to this theory seminar or CAPA seminar. Today we have the pleasure of having Violeta Gonzalez Perez, an old friend um, of studies. And well, let me just spend 1 minute on her trajectory so that you all know what she's about. So Violeta studied here in the University of Zaragoza, and then she moved to Barcelona to her PhD with Fernando Castander on I think galaxy evolution and galaxy determination, and since then has been postdoc in very interesting institutions in the UK and in Durham in the Institute of Computational Cosmology in Portsmouth and in other places which I dare not remember. And since then, she has been becoming more and more of an expert in the study of galaxy evolution and using numerical simulations to understand the evolutions of galaxies, dark matter in galaxies. And lately also on how these, I think, galaxy evolution knowledge can be used to understand better cosmology, dark matter, dark energy, and so on. And we are extremely pleased to have you here to tell us a little bit about your latest results. Whenever you're pleased.
Okay, thank you very much, Javi, and thanks for letting me come in here and talk to you. I have tried to make like a long introduction for everything, so I hope the concepts are a bit more clear. So the title is Star Forming Emission Line Galaxies as Cosmological Traces at Redshift 1. Let me start by saying that redshift is just a measurement of distance from us. So the higher the number, the farther away. But it's also a measurement of the cosmic epoch. So again, the higher number is going to be closer to the Big Bang. So what is the universe made of? How quickly is it expanding today? And how much does that expansion rate change over time? These are, I will say, fundamental questions. And maybe the fundamental question is the first one: what is the universe is made of? That we are concerned with in astronomy and well, in cosmology, I will say, but also in astrophysics. No, this is kind of like one of the biggest still mysteries that we have to solve within physics. So the idea that we have in the best model that we have for the formation and evolution of structure is that there was a big bang, and then there was a period, a very short period of inflation, and then the structures started to grow at some point. So at some point, you start to form stars that give rise to galaxies. So basically, what is driving all these processes, and how is the space expanding, right, with time, is what many of us want to understand better. Last summer, the Sloan EBOS survey finished, and I'm going to start this talk by telling you about the main results from this survey. So here you have a picture of the Sloan telescope, that is a 2.5 meter telescope in Apache Point in the States. So it's not very big, but it has sampled the whole sky throughout like a bit more than 20 years. In the past kind of 10 years, this spectrograph was added as one of the instruments in this telescope. You cannot see the details, but it's just a spectrograph with a lot of fibers to measure spectra from many galaxies. So this was one of the surveys within this bigger survey called SLOAN, SDSS. And this one is called EBOS. I'm going to mention several times EBOS because the target for EBOS was cosmological studies to understand better the composition of the universe, in particular the nature of dark energy, to make it more precise what we know about it. So in all these years of working with Sloan and EBOS, they have measured 2 million galaxies. The idea here, you see on the bottom axis time from the Big Bang. So we start at 0, then we have the first light coming from the cosmic microwave background, the formation of some stars, and this is us today. And this will be the part of the universe that Sloan can observe. So this is kind of the whole like observable universe. And here you have like the map of the galaxies and first stars, etc. So this is kind of like the idea for EBOS, to have a 3D map with as many galaxies as we can, to be able to establish how the universe was expanding at different cosmic times. This is a video, if it starts, of all the different stages of Sloan and the different parts of the sky that were covered for all these years. And well, what you can see is that there's a large coverage, and what I'm interested in, I'm going to be talking a lot about today, is this blue type of galaxies, but I'm going to come back to them. This is just to give you an idea of how the survey is covering, is making this 3D map of galaxies. So each point here is a galaxy. The different colors just are showing different types of galaxies or tracers. I will talk more about this in a moment. The main result from this survey, it might be this plot, right? That is showing, this is the curvature of space on the x-axis, and this is the Hubble constant. I put here that sometimes we measure the Hubble constant, we call it H, capital H, but sometimes we also quote it as 100 times little h. You are going to see this little h afterwards in units, so yes, so it's clear. This Hubble constant is measuring how fast is the expansion of the universe at a given epoch, basically. So this first contour is the error bars that we had in 2010, so 10 years ago. And the blue line is basically what we had last summer when this project was finished and this data was released and published. So the important thing here is basically the curvature of the space is flat. And another result from this survey is that lambda CDM, so the cold dark matter paradigm for the standard cosmological model is still heavily well encouraged, or this data is telling us that that's the best model still. What else? There has not been detection of neutrino masses yet, so this survey also put some upper limits constraints. So this is kind of the summary of the results from this survey. One particular thing, well, this is all, we have still this picture then from this survey, that 68% of the content of the universe is dark energy, 27% is dark matter, and the ordinary matter is about 5%. One particular point that is quite interesting, because it still is in conflict, and the conflict now is bigger, is if you measure, this is kind of a measure of how big is the universe at a given time. And this is this Hubble constant that I told you about, that is measuring the expansion rate at different epochs. So what you can see here is that the BAO here indicates the measurements from this survey that I'm talking about, Sloan plus EBOS. So that's kind of the constraint of these parameters. But you have to anchor this measurement at some point to actually measure the size, not relative sizes of the universe, but an actual size. So if you anchor this measurement using the first light coming from the cosmic microwave background, what you get is this contour. If you instead anchor this measurement on the distance ladder, so starting from our galaxy, we go to the next galaxy using variable stars, and we are measuring distances. If you do that, then you get this values for the Hubble constant. So there is a big tension, and the tension is there, and it seems that it's not going anywhere. It's not due to systematic errors, that's at least for the high redshift or later cosmic times. Could be maybe systematics in our close by measurements, maybe, we don't know, but there might be also some new physics going on here. So this tension that we thought it was going to go away, it has not gone away, and it got a bit worse because now the error bars are smaller. So this is also quite an interesting thing from this survey. This survey is positioned here in this plot around here. So this is the number of galaxies in as a function of years. These were called, SLO and EBOS is called stage 3 cosmological survey. That has to do with the precision that you are measuring cosmological parameters. And this survey, basically the measurements have like 1% error. There's a whole lot of surveys that are coming, like DESI, and this is for DESI, Euclid satellite, and other ones that are stage 4 surveys, meaning that they want to measure cosmological parameters with sub% accuracy. And you see that for that, you need even more galaxies and covering more volume, right? So this is starting, DESI has already started actually, Euclid has not been launched yet. So this is the next, the future of all these, trying to understand dark matter and dark energy using galaxies surveys. So DESI, that is the thing that has just started and is kind of continuing the effort from SDSS EBOS, what I just talked about, is also measuring the same type of galaxies. So here at low redshift or close to us, we have just all galaxies that you can see, just limited in brightness. After that, you are looking to big red galaxies, just because otherwise you don't see them. And all this region, you need to explore with what we call emission line galaxies. I'm going to talk more about this, but they are very interesting because they are measuring this part of the cosmic time when dark energy started to be more important. And then we have also quasars. Uh, Probing much higher redshift, so much closer to the Big Bang times. This is a plot showing you just how the critical density for the cosmological constant is changing with time, or the age of the universe. And this is just showing you today we are dominated by the cosmological constant, that is basically dark energy. But when it started to be kind of important is at redshift 1 or a bit before 1, when the universe was kind of half the current age, right? About that time. So there are many surveys that are very interested in this epoch just for this reason. How these surveys work? First, you have images of the sky, like this one, and then you choose where you're going to put your fibers to get a spectra. This is showing you a spectra. Why do we need a spectra? Because we want to measure very precisely the redshift, the distance to us. This is the definition of redshift. So it's the wavelength observed divided by the rest wavelength. So you choose your targets in a smart way. So you are trying to focus on these either emission line galaxies that I'm going to talk what are they, or the luminous red galaxies. So you have a lot of galaxies. So you are populating your 3D map in a dense way. So you can afterwards have very precise cosmological measurements. So if you're measuring things below redshift 1, this has been used widely in, for example, EBOS. The biggest sample was what we call luminous red galaxies, but this plot is showing you the number of this type of galaxies as a function of redshift. and you see the decline of these galaxies at the moment that you arrive to redshift 1. That is when I said that the dark energy starts to be very important, and therefore is a very interesting part of the cosmic epoch to explore. And here you have a typical spectra of these galaxies at this redshift. Basically, you don't see anything. The red line is the sky, and these lines is very difficult. This is just to show that it's very difficult to determine redshift when the spectra is so kind of smooth. Uh, this is going back again to Sloan, EBOS, just to show you the different types of tracers that we have used. And as I said, I'm going to focus on this blue patch that corresponds to young blue galaxies. Here you have like an example, how did they look like. So this shows some old now surveys, but also some upcoming surveys for galaxies. So this is cosmic time, and this is the area that they cover, and the number of galaxies is shown by the thickness of the line. All of these that I'm marking are targeting emission line galaxies. Okay, so there's a huge interest in a type of galaxy that allow us to sample the redshift 1 or around 1 when dark energy started to become really important. So why star forming emission line galaxies? Or in this talk, I'm going to call them O2 emitters also in distinctive. Yeah. So this is the composite spectra of a emission line galaxy, of these ones that are being targeted by Sloan EBOS. And what you can see, the continuum, this part, so this is flux and this is wavelength. The continuum of the spectra is very flat, but then there are very strong emission lines. And as you can see, the O2 line is particularly strong. And not only that, but this is a doublet. There are two lines here. So that's why using O2 lines is very, very powerful to measure fast redshifts. Because if you only measure a single line, maybe you could think, I'm not sure if I'm looking to an O3 line or an O2 line or an H alpha. Maybe you don't know, but because we have a doublet, you can match it very nicely. This is an image from DESI. I didn't put this from John Mustakas, and here is showing you that we can fit the spectra really nicely, quite fast, relatively fast, so you can get many galaxies with their distances to populate this 3D map that we need to do cosmology. So this is the power of the doublet for DESI. And now I want to talk about what are emission line galaxies. Then I have shown you a spectra, but why this spectra is like this. So the background that I'm showing throughout all the talk, the images are from decals, is one of an imaging survey. And these things surrounded by the green circle are emission line galaxies measured by EBOS. So these galaxies are redshift 1. So when the universe was like half its age, current age, like 6 giga years, this is how they would look like if they were closer to us. This is an image for the antenna. And what you can see is these pink regions are these regions with very strong emission line in the spectra. These are due to strong, well, big stars heating up gas around them. So basically what this indicating is that you have a strong star formation. So this antenna, if you put it at redshift 1, this is how you see it, just like a blob. But you can still detect the emission lines in the spectra. So the question, my work is basically trying to answer this question of how do emission line galaxies trace the dark sector of the universe. I have given you now the context, so now I'm going to talk a bit more how, well, what do I do basically? To answer this question, what I use is models. I want to use models in a cosmological context, so I need to focus in samples, big samples, that are big enough to cover the observable universe. So what I put here, like 10 to the 10 galaxies. What I'm showing here is this now is really old plot, and I didn't give credit, but sorry about that. These are observations in blue, and here in red, you have simulations. And this is quite old now. It has like 10, 15 years. And you can see that the simulations, this is dark matter only simulations, but these ones are already reproducing quite nicely the features that we observed. So we have a good grasp of how to do dark matter only simulations to reproduce what we observe. But I'm not only interested in the dark matter alone. I want to also explore the connection between galaxies and dark matter. So then what processes do I need to model? This this plot is showing you the observations for the number of galaxies that you found. So this is basically a histogram normalized by volume and difference here. This in the x-axis you have stellar mass. So basically it's a histogram of the number of galaxies per unit volume as a function of beings in stellar mass. So this is what we observe, okay? This is observational data. If now I take a dark matter only simulation and I measure the same thing for halos of different masses, this is what I get. You can forget about this part that's due to the resolution of the simulation, but basically it's a straight line in this plot. Has nothing to do with the shape that we see in the observations, right? Why? Then because I can even normalize this to match this knee, but I will still have too many small things and too many big things. The point is, in dark matter only simulations, you are making things interacting only gravitationally, right? You have like balls of billiard just colliding. That's how they work, the dark matter only simulations. But if you're interested in galaxies, there are other things that matter. And this is showing you, this is the same plot as above, but just divided by the stellar mass by the halo mass. So if in this plot, if the visible matter was following exactly that of dark matter, so if only gravity was important, this would be a straight line. But that's not the case, and that's because all these effects that I'm putting here are taking place in different scales in mass. So we have reionization affects the having or not having galaxies at certain masses. Also stellar winds, supernovae. We have disk instabilities also affecting how many galaxies we have at different masses. And then superwind, gamma rays, thermal conduction, and also AGN feedback, well, what we call usually feedback. Um, okay, so we have all these processes that we need to model if we want to understand galaxies. On top of that, we also can ask what are the scales that are relevant. And I have talked about these emission line galaxies being galaxies with a strong star formation. For star formation, we are interested, or for for star formation, we will be interested in parsec size regions. If we are interested in galaxies, then it's tens of kiloparsecs. The observable universe goes to gigaparsecs. Plus, as I say here, subparsec processes are affecting the evolution of galaxies because you have supernovae that are going to explode, etc. So we have to cover a large range of scales in size, and also to cover a vast number of different processes. Given that we have finite resources, there are different models depending what is your question, right? So if you want big volumes and you don't care, well, you cannot care too much about what's happening at very small scales, then maybe you will use one of these empirical models, helicopation models, halo abundant matching, etc. If what you care is about knowing exactly what happens with the gas when you have a supernova exploding, you have to go, for example, to hydrodynamical simulations. No, that in let me explain this type of models in two, that is more like more physical models and more empirical models in this size. But I have also created this difference between, these are what I call in parallel models. So hydrodynamical models, the way that they work is that you start with a box that contains dark matter particles, star particles, gas particles, black hole particles, right? And then you let all these particles evolve together, interacting among them. And then all the rest of these models, they are what I call in series, because first you are creating a dark matter only simulation that is represented with this image from the millennium. And then on top of that, you use some type of model to create galaxies. So all these models are different ways of doing this step of populating galaxies on top of the dark matter only simulation. In this talk or in my work, what I have used basically semi-analytical models of galaxy formation and evolution, and halo occupation models that I will be talking about later. The simulations that I have been using, they have different box sizes or different volumes. They are covering different volumes. Outer rim is a 3 gigaparsec side simulation, and so you have an idea how it's compared with other simulations. Multi-dark, I'm going to talk also, that is 1000 megaparsec. This is already there. These two are quite good already in terms of reproducing the scales of the observable universe. This is the Millennium, that is 500 megaparsec. They are semi-analytical models with galaxies populating all these three dark matter simulations. And then Bahamas is a hydrodynamical simulation. This is the largest so far. So this is the largest volume that has been covered with hydrodynamical simulations. And that's Eagle, that is similar to Illustrious TNG. So you see that the volume that the what they call cosmological hydrodynamical simulations is really tiny compared to what we can achieve if you are doing some empirical modeling for the galaxies. What I show here is, of course, that the mass of the minimum simulated dark matter has to increase because the limit is on the amount of these dark matter particles. When I say dark matter particles, I'm referring to dark matter corpuscles or billiard balls, if you want, because in here in Eagle, they are like 10 to the 6 solar masses. In Outer Rim, they are of the order of 10 to the 9 solar masses. The complexity of the galaxy formation model has to be not too high in this big volume because otherwise we will never finish doing the simulations. Okay, so coming back, those are the tools that I use. Basically, the way that I model, the models that I use to know about galaxies as cosmological tracers. So then coming back then to this, how do emission line galaxies trace their matter? One of the things that I'm going to talk about is this emission line. How do we model this? There are different ways to do this. You could assume that emission line galaxies is the same as saying star forming galaxies. You could relate the star formation rate to the O2 line that I have already mentioned. You could also assume one typical region for star formation with different metallicities, or you could do a coupling with photoionization codes. That's like the most complex one. I'm going to start talking about this having a typical star formation region. And I'm using, these are the details of the type of star forming regions that I'm using, but not super relevant. I'm using a semi-analytical model for this, the results that I'm going to show you now. This is a fly through with the semi-analytical model. So on the right, you have the dark matter only simulation, and on the left, you have where are the galaxies. So as you see, basically space is empty. And even if you have, in some cases, dark matter with some potential wells, this has not been enough to form, for the gas to become dense enough to form stars and galaxies. Let me just draw your attention to this filamentary structure of the cosmic web. What we call the cosmic web is because you have, I cannot pass the mouse on top, doesn't matter. You have in the dark matter only simulation, you have all these kind of structures that are elongated. So it looks a bit like a spider web. So we call it the cosmic web. So using GALFORM semi-analytical model, I construct a sample of galaxies that are mimicking the observed ones for emission line galaxies. This is showing you a normalized histogram of how many galaxies there are per luminosity on this O2 line. The only thing that you have to take from this is if you compare the solid lines with the symbols, is a comparison between my model and the observations. It's not perfect a match. It was not tuned to reproduce this, but the point here is that they are in reasonable agreement with the observations. And with this, I can explore them further, how is the connection between these galaxies and the dark matter. Um, I'm going to talk now about making samples that are fixed in number density, because I also want to explore how different are these emission line galaxies with respect to making a cut in a stellar mass or star formation rate, different quantities. So this plot is showing you a cumulative histogram. This is in stellar mass. So what I do is basically making several cuts in number density here, and mm, that corresponds to a given stellar mass. So that's how I construct. So basically I make a cut in stellar mass. So I have the same exact number density for all these samples. And I do the same for star formation rate that is here in the x-axis and the O2 luminosity function. So basically I'm going to have same number density, but selected in different ways. So I can compare them. One thing that I explore with these samples is how these emission line galaxies selected in different ways are populating the underlying dark matter. So in gray, you have the distribution of dark matter, and you can see here what I was saying of the filamentary structure, this kind of spider web structure. So that's dark matter. All the symbols are these emission line galaxies, or just galaxies selected at a fixed number density in the way that I showed before. So, okay, here you can see some things. The blue points seem to be in not as dense parts as the red points, but it's a bit difficult to see like that. So to quantify it, I measured the cosmic web using a couple of algorithms. So this algorithm VWeb is using the shear tensor. This is also showing you the distribution of dark matter. In red you have like the nodes, the most dense part, and in black you have the voids, the least dense parts. Another algorithm that we have used is pweb, and then this is showing you the density. So basically we quantify if something is very dense and we call it node, not so dense and we call it sheet. And then we have filaments, and sorry, this will be filaments, sheets, and then voids. We just quantify the cosmic web in 4 things. Basically the names are here. So this is the most dense, the knots. Then we will have filaments, then sheets, then void. But you can think of this as how dense. This is least dense, most dense. And this is the fraction of galaxies per structure in the cosmic web. The point that there are many things here, but the point to focus is that the red bars are a bit different from the blue and the green. The blue and the green tend to be more often found in sheets, for example, and the red things are at least for this one, it is more often found in knots. This has implications because this means that these emission line galaxies or star-forming galaxies, they tend to live in less dense environments. And this has also implications on how galaxies form and evolve. Another thing that I have explored is exactly how these type of galaxies are populating halos. So this plot is showing you here the mean number of galaxies of a given type, so divided by the number of halos. So here you have the mass of the halo, and this is basically number of galaxies divided by number of halos in a given bin in mass. the point here is that if you're making a cut, so these are all samples with equal number density. If you're achieving this equal number density by making a cut in stellar mass, you get these red lines. And I want you to focus on the dash line. That is kind of the, well, the ones that go to the middle, the center of the halos. So in the case of making a cut in stellar mass, this goes to 1, more or less. um, and it has this form of like a step function. If you are looking to start forming galaxies, that's not the case. If you look to the dashed lines, they go much below 0. So remember, this is a log scale, so 0 corresponds to 1 galaxy per halo. So we don't achieve that. So the shape of this is very different. It's very different the way that they populate the halos for this reason. So that's the main point that I want to make from this plot. And then we can look also to the clustering, how they are clustered in the sky, these different types of galaxies. So what we are I'm showing here is the log of this two-point correlation function. The two-point correlation function, you can think of, well, this is one definition that we use for the simulations, that is measuring the pairs of galaxies divided by how will be a uniform Poisson distribution. So we are basically comparing the whatever distribution we have with a Poisson distribution in the sky. So a uniform distribution, if you want. So that's what this is measuring. And you can see here the black is for the dark matter. If you select, remember that all this is fixed number density, so it's the same amount of galaxies per volume. But if you do the cuts in stellar mass, these are much clustered than the dark matter. However, star-forming galaxies, they follow quite closely the dark matter distribution. There are big difference in the one halo term, however. Let me explain this a little bit. If you are looking, so this is separation. So you are counting pairs of galaxies at different separation. So if you are looking to galaxies that are separated less than 1 megaparsec, basically you are looking to galaxies that they live in the same gravitational potential well, that usually we call it halo of dark matter, right? So you are looking to the what we call one halo term because you are counting things in the same gravitational potential well. If you're looking above 1 megaparsec, then what you're counting galaxies in different halos. So this is why it's called the two halo term. There are big difference, I was saying here, when you're looking how galaxies are distributed in one halo. If you make cuts in star formation or in flux on O2. So that's a detail that might come to be important. So the summary of this part is that the properties of star-forming emission line galaxies and mass-selected galaxies are very different. Galaxies selected by their O2 luminosity are very close to star-forming, but at the smaller scales, we find differences. And the star-forming galaxies tend to live in less dense regions than mass selected galaxies. Okay, I'm going to go a bit fast. Maybe how much does the modeling of emission lines matter? I think I'm going to skip a bit this. Just I give a brief summary saying that we use a very simple approach and the most complicated approach that we could. And I don't explain this. And just to let you know that what we found is that if you're interested in, this is similar to the other plot, just so it's measuring how clustered your galaxies are compared to a uniform distribution. The point to take from this, and is the main result of this paper from with Ginevra Favole, is that if you're interested in large scale structure, it doesn't matter too much how you model your emission lines or your galaxies with emission lines. If you're interested in redshift space distortion, small scale clustering, then you have to worry about this. So that's the main point from this part. And then what we did then is to use the results that I have been talking in detail about from the semi-analitical model and use them to populate a very large, the outer rim, the big dark matter simulation that I showed you in the introduction, with a much simpler model, so we can try to understand what systematics are we introducing on the cosmological inferences by making different assumptions on the galaxies that we are using as tracers. So for this, again, this image, we are using kind of the easiest, the simplest empirical model to do this, so we can populate fast a large volume. So we use this outer rim simulation that is 3 gigaparsec size, and then we use what we call a halo occupation distribution model to populate it with galaxies. And we use the information that we had from the semi-analytical models. So we varied a lot of properties for this paper with Santiago Avila. I just show you one example that is varying the halo occupation distribution. I have shown you this before. So basically in the y-axis you have in log scale number of galaxies divided by number of halos per being in halo mass. So you see that here we have different shapes, and you see how changing these shapes affects the clustering at the small scales in the one halo term. This is one example. We have changed also how to distribute the galaxies within halos, and the velocities, and the probability of finding galaxies in one halo. So we varied all these. We created like a grid of models. So the people that are doing the cosmological analysis could use all of them and repeat their cosmological analysis using different universes. And the only difference of these universes is the assumption of how we populate the dark matter halos with emission line galaxies in this case. And this is the result that they obtain. On the y-axis, you have different cosmological parameters measured with, well, both BAO, baryonic acoustic oscillation, and redshift space distortion. And here on the x-axis is simply indicating the different models that we use. So we changed the type of model to populate the dark matter, and then we give to the people to run the cosmological analysis and to see what happens. What you see is that there is variation depending what we are giving them to do the cosmological analysis, but you can appreciate that all these dots are within this gray band. And the gray band is the system, well, the statistical error basically for EBOS that is below 3.3%, and it was estimated in ALAM 2020. So the point here then is that all these points are within the statistical errors from this analysis, for EBOS Sloan that I introduced before. So then we don't need to worry about all these issues for galaxies. This was all good for Sloan EBOS, but the point I also made in the introduction is that the next generation of surveys like Euclid and DESI, they are going to go from precision of 1% to sub-percent. So if here we reduce the error bar, the statistical error bars, we might have encountered that we are limited by systematics due to our ignorance about galaxy formation and evolution. So that's work to be done in the future. And I will say the takeaway message from this talk is basically that, the last one, that the cosmological measurements from Sloan EBOS that finished last year are insensitive to the details of galaxy physics, but this might not be the case for coming surveys. So we need to continue working on this topic. Thank you very much.
Very well. Thank you very much to you, Violeta, for this very nice talk and this huge amount of work. So if you're happy about it, we will have some time for some questions.
Sure.
And yeah, I wonder if Siana, Diego has disconnected now, have some questions. If not, I have a very nice list.
I'm here.
Do you have any question, Sienna, or some comment you want to make?
Well, only, well, of course, I am not the expert on this subject. I have not idea about, really, but I have a curiosity. So, Violeta, at the beginning, well, most or less at the beginning of the talk, you show the plot with the number of galaxies versus the mass, right? Or something like
Yes,
this,
right.
in which you have a big disagreement between the experimental data
Ah,
you have and,
this you mean, no?
yeah.
Yeah, yeah. But the model was not tuned to reproduce this specific thing. So, okay, what is your question?
So the question is, so how can you explain this big disagreement? Is because of the simulation or what? What is the reason for this?
Trying to mimic observations is tough.
Okay.
So I didn't put these things, but I mean, the model was calibrated to some observations at redshift 0.
Yeah.
And then what we do is to try to mimic the surveys, and this is done, this is colors. So this is kind of comparing parts of the spectra and then making the similar cuts to what they do in these surveys, plus a flux cut, but there are many things going on the trying to mimic the selection of the observation. So we could do better. Like I could just try to fit the observations for one survey, but I don't think it was, I didn't thought it was worth to do that, in the sense that the numbers are kind of reasonable enough, are good enough, because there's also the issue with the dust. This line that is dotted here doesn't have dust attenuation,
Yeah.
and if I change the model for dust, this also is going to change. So uh, kind of like I don't think it's worth my time to try to really reproduce one survey for this kind of general study that I just want to have an idea. If I want to produce more catalogs specific for one survey, I should do that. Yes.
Okay. Thank you. It's just was a curiosity about the divergences you have. Okay. Thank you.
But yes,
Thanks a lot.
going a little bit further with this graph, is so you have only mentioned just cuts and essentially sampling, right? Choosing your sample or something like this. But are there some specifics of your model? So maybe you have to add more parameters to your model, or you have to complexify a little bit your model to improve the agreement or so.
No,
And
no.
maybe these parameters are relevant for later.
So I have been focusing mostly on these samples that are just one simple cut, but I did a whole study making these more complex cuts. The semi-analytical models, they have already many free parameters. Um, there's a lot of degeneracy between them. So at the end, you are kind of constrained by feedback from supernovae and AGN. Kind of those are the main two things, but there are more things going on. So it's already pretty complex, this model. So I don't think I need to add anything else. It's just, it's difficult to, for example, to constrain the dust attenuation model if I focus only on that part. So yeah, I don't think I need to add more things. It would be maybe better to find better constraints for the model.
Very good.
Can I ask a question?
Sure.
Sorry, I joined a bit late, and also in your conclusions, my connection dropped. Can you
Oh, okay.
can you go back to your conclusions? Sorry.
Sure. It was just a repetition of what I said before.
Maybe a couple of slides before, the one with the constraints for data.
This is this.
Yeah. So you are trying to constrain sigma 8 with this data sample. Am I correct or no?
Well, this is more like a measurement for the how big are the systematic errors. So, I mean, let me maybe show. This is coming. I have been participating in the EPOS collaboration. These are the main results from the collaboration, right? But the group that were doing this analysis, the cosmological analysis, what they did was to run their analysis using different mock catalogs of galaxies. So just to explore, we know exactly what is the cosmology that we are giving them and exactly what we have given them. So you can explore the systematic errors if you are using different assumptions for the galaxies, right? So that's basically what is shown in that plot, this one.
Okay.
So it's
So
repeating exactly the same pipeline for cosmology analysis on different mocks. So here are all like, okay, whatever number is on the x-axis.
okay.
Yeah.
And
I
then,
was wondering if you had done a full MCMC with all the system, with all your parameters and also cosmology parameters and everything. That's what you showed me, I guess.
There is a MCMC, but no, they have included this. Yes. So the error bars here have been taken into account properly.
so your the systematic presented in this talk is already included in the results of EBOS.
Well, yes. The problem, I mean, yes, but it doesn't matter, kind of thing.
But yeah, it's much smaller, but it will be very relevant in the future.
Yes.
And so the question is, what are we going to do in the future? So do we have to improve very much our semi-analytical models. We have to calibrate much better the hydrodynamical simulation, also the models with hydrodynamical simulations. What is the plan now?
I mean, what we are doing is kind of repeating the same, but for DESI, and see if if it really matters, how much it matters, all these things, and exactly what matters. Because we thought maybe the shape that I have showed of the halo occupation distribution was the important thing, but maybe that's not actually the main point, and is the distribution within the one halo. But this is because this matters here a bit because it's the redshift space distortion part, so the one halo term part. If you're worrying about BAO, all this doesn't matter. So you could have a good measurement of cosmological parameters without really worrying much about all this. There's one thing that I have not touched, and we need, as like the community are starting to do, that is, I have been using what I call these parallel models, that I have my dark matter only simulation and then I put the galaxies. However, if you run hydrodynamical simulations, it has been shown that the presence of baryons are affecting the halos.
That was my next question.
And we do need to explore this in more detail and how it affects afterwards what effects has on cosmology. Yeah.
So we are talking about feedback.
But not quite. I mean, yes, but the feedback that is kind of like is kicking out dark matter particles from halos.
Exactly. So how the baryons affect the structure of the dark matter, right? Which
Yeah.
is
There are several studies already showing that it does matter for small scales. For large scales, is I would say is not that relevant. Yeah.
And what I was thinking is I recap more or less the conclusions of these studies, that they typically talk about the centers of the galaxies, big ejaculation of dark matter, softening of the dark matter distribution at the core, and so on. But when we talk about these star-forming regions or these emission line regions, you said they happen now in low density environments. I guess because in the very dense regions were shining in the past or something like this, or there's some self-quenching process or something like this. But nevertheless, it looks like if you are focusing on emission line galaxies, you might not be so affected by this feedback. Is that true?
No, you are, because they tend to be smaller galaxies. So let me go back to this one. So here you have on the x-axis the mass of the halo, and if you are looking to big red dead things, they tend to be in larger things, so in larger halos, right? Because you start this line at like close to 10 to the 12, and these emission line galaxies or star-forming galaxies, they start to appear in 10 to the 11. This means that they are more affected by supernova feedback or winds. that they can be more affected by that.
Yeah,
Plus other
you mean
effects
because they
that
are
I have
smaller.
not talked about. Sorry?
You mean because they are smaller?
Exactly, they are smaller. So any wind is going to affect more the gas.
Okay. I somehow got the picture that you showed us before, and with these emission line regions were more or less in the outskirts of this galaxy.
I think I'm talking not about star forming regions, but whole galaxies that are dominated by the star formation rate. Sorry if that was not clear, but I think you can see it here by eye that there's more blue points. So the darker the color in gray is the denser region for that matter, right? So there's more red on denser region than blue.
Mhm.
The blue tends to be, I mean, by eye is not super easy to see, but
No, there's something
yes.
to it, yes.
But these are whole galaxies.
Yes, so this is more or less your. Is this a picture supported by hydrodynamic simulations?
Yes,
Really,
yes,
the
it is.
whole star is shining more homogeneously in emission, so in oxygen lines or whatever. It's not that the emission is concentrated in very few spots.
Are you asking about like inside galaxies where this happens?
Yeah, yeah.
But I mean, for this purpose, you don't care about the inside of galaxies, right? Because you cannot resolve them individually. So everything that I have shown is for like a whole galaxy, like
Yeah,
the
it's
picture.
understood. Yeah, but
So I have not talked nothing at all inside galaxies except when I was showing the antenna.
no,
But
sorry.
these are
I only brought the thing because I thought we were talking about baryonic feedback, and baryonic feedback can happen very differently uh, in the center of a galaxy and in the outskirts. I thought.
yes.
So,
But okay, the thing here I think is mixing like the large scale environment, that is what I'm showing in this plot, and the galaxy itself. Yes. This particular picture of blue, like star forming things are in less dense parts, like filaments. This is, we agree, everyone agrees on this. Observations, hydrodynamical, semi-analytical. So this is good, let's say. Now, if we talk about how the feedback is going to affect the dark matter, there are two issues. If you are smaller, you are more affected by supernova feedback, but that I'm talking about the gas. The problem also is because the halo is going to be smaller. It might also kick some. I'm not clear. I don't have an intuition because there's not much done on this to yet have an intuition on what's going to happen. The semi-analytical model is not solving the internal regions of galaxies. Therefore, there's one that does it, but in general my model GALFORM doesn't do it. So then I cannot really compare with hydrodynamical simulations, and I don't want to use semi-analytical model for that purpose, because for that purpose I will use a hydro simulation. If you're interested in knowing what happened where for a galaxy in relation with feedback, personally use as a hydro simulation, not a semi-analytical model. Yeah.
it makes sense for sure. But surely they are very informative to calibrate, or you're just probably to even invent new parameters for the model, right? So in a sense, they have to be the inspiration for your models.
I would say all models are useful. It's just depending on the question that you want to answer. You should use your correct tool, right? So semi-analytical models are awesome to explore the parameter space of different options, because you can run many options for feedback or other things and then explore what happens. Plus populating big volumes, much bigger than you can with hydro. But if you want to go as we did with to outer rim, it's even better, like easier to have a halo occupation distribution, right?
Reasonable, yeah.
Sorry?
Sounds very reasonable. Very well. So is there some...
Can you say a few more words on the dust? Because you kind of avoid it, but it may change your results, or it's just within the error bar. So.
No, well, okay. I can. I don't have here the slide, but in the model, what we have is two types of dust. One is in molecular clouds, so that's the regions where you have star formation, and then we have diffuse dust. This is informed by observation. So in observations, that's how we think the dust is distributed. We have explored the dust model in detail in a couple of papers. The model that we have, it seems to work quite adequately for at least normal galaxies at high redshift. The problem with the dust modeling is very difficult to pinpoint it observationally. So even if I tell you that the dust is the dust model is reasonable, it might be wrong. I mean, just because it's difficult to observationally, it's very difficult to measure it for galaxies at different redshifts and in a range that is big enough to have a good sample of galaxies.
Okay.
I don't know if you want to know more about dust.
No, that's fine. That's fine.
Okay.
Perhaps just a very quick and general question. So you have mentioned that at up to very small redshifts, we have a complete sample of bright galaxies for these studies of the expansion of the universe. But now we are very much looking forward to have many more galaxies up around redshift 1. And I was wondering what happens if we just get a complete set up to redshift 1, more or less. So what would be the statistical error bar in the cosmological parameters if we had such a gift?
We hope that very little. I mean, and DESI has just started, and in 1 month it has covered. I mean, it has measured as many galaxies as EBOS in 1 month, because they changed the way that the spectrograph works, and now you place the telescope and then you measure 5,000 spectra. So in a month it has like overseen EBOS. So it's going to last DESI 5 years. And the statistical errors, I think they are going to be ridiculously small. I cannot remember now the number, but very small.
Okay. But then systematics really come up to the surface.
Yes, systematical are going to be important. The emission line galaxies is a difficult sample because it's just a difficult sample because they are star-forming galaxies, and there's many details that go in these dust matters, and how strong is the line. It depends on how many stars are being formed. It's not like with red bright galaxies is closer to have a complete sample of everything that you can see up to a certain brightness. But here is more nuanced, the way that you select. So already to have these window functions for the selection of the galaxies is even harder than for the luminous red galaxies. So actually in DESI, emission line galaxies are lower in priority than luminous red galaxies and quasars, just because they are much easier to understand the systematics of both of them.
Mm-hmm. Very nice. So why insisting so, as a summary, why insisting so much in line emission galaxies if they are more complicated and more systematic dominated?
Well, because you can see them in this part of the redshift, the cosmic ages. That is the start of the domination of the dark energy. So without them, you are not going to probe that part.
Yeah, okay. That's good enough for motivation. Diego, Sienna, we haven't some other question?
No, yeah, as I said, I'm sorry, I joined a bit late.
Don't worry. Thanks for coming, everyone.
Yeah, if not, so
No
then,
sense to you.
We thank Violeta very much again for this very nice talk and this discussion afterwards. And we hope that we can have our little discussions in presence, not telematically in the near future soon. And I forgot to say in the introduction that she is now in Madrid with an Atracción del Talento fellowship. So she will be
CIEMAT, or where are you? No, in the Autónomas. Oh, okay.
the Autónomo. So she will be just one stone toss from us. So
Yeah.
we might have.
By the way, we I don't know if you are aware of it, but we have a cosmology meeting every 2 years in Benasque, and it was supposed to happen this year. But due to COVID, we made do it maybe next year or in 2 years. So well, I guess now we are all in Spain, so it will be.
Oh, Diego, you're in Spain. I thought you were in UCL still.
Today is 1st of July. Today I'm officially in Autonomous University of Barcelona.
Okay, okay.
Yes.
Good.
Yeah, good news.
I'm slowly coming back.
No, today I am next to Javi. I am in the office next door at Tusiana. I'm in Zaragoza today.
Okay.
Exactly. I just stole some cables from your secretariat.
Okay. Wow. Okay.
Cool. Yeah, we'll try to go to the Benasque meeting maybe next year, I guess.
Great.
Good.
Okay.
Recording now.